Once upon a time, our world was predictable. The tides came in, the sun came up, the world went round. Just as we had always known. Then all of a sudden, physicists were launched into the darkness, into unknown territory, with discoveries so absurd that maybe if they'd known what they were going to find before, they would have turned a blind eye. They unravelled nature's most shocking secrets, leaving physicists to exclaim, "I do not like it, and I'm sorry I ever had anything to do with it. And if that turns out to be true, I'll quit physics." So what was it that flustered all these physicists, causing the biggest furore in scientific history? You probably won't believe what you're about to hear. You'll think, no, that can't be right. And if you do, you won't be alone. One of the greatest minds of all time, Albert Einstein, exclaimed the exact same thing.
You look around you and the world looks a certain way. Does it look the same way if we go to large scales? Does it look the same way if we go to small scales? And the answer is no, resoundingly no.
When you're talking about the quantum world, what you're talking about is things of the scale of atoms, subatomic particles, photons of light. So you're talking about something vastly smaller than anything we're familiar with. And pretty well everything really is different.
The beginning is usually a very good place to start. But skipping past what is probably the greatest discovery of all time, the discovery of the atom, and then the discovery of the now familiar nucleus of protons, neutrons, along with its orbiting electrons, and we can start to learn about some of the really crazy things that happen all the way down there in the quantum world.
Around the late 1800s, people thought they understood everything. And if you look back, while they had very complete theories for what was around them in terms of extending that to other realms, not even close.
Basically, you can't use the usual equations that we'd use to describe objects, balls and missiles and things rolling down a ticker tape and people and cars, which is sort of the laws of mechanics that you learn at school. None of that worked when you describe atoms. You had to come up with a new kind of mechanics, hence the name quantum mechanics.
And really, the concepts that propagated as a result of this were radically different from those of classical physics. It even made science fiction look tame. One is the fact that all particles, get this, behave like waves and vice versa. What does this mean? Imagine ripples on a pond. If there are two ripples, for example from these stones I throw at the same time, the crests of the waves where they meet reinforce each other to produce an even bigger crest, but if a crest of one coincides with the trough of the other, they cancel each other out. This is called interference. Now if we create water waves like in a ripple tank at school, and in the middle of it is a screen with two vertical slits.
As the waves go through the two narrow slits, they squeeze through the slits and then they spread out. And where the waves overlap and interfere, you get sort of bumps and ridges and it gets all sort of messy. And if you have on the back screen, you see what's called an interference pattern, where the waves interfere. So you get patterns where the waves are very strong and patterns where they cancel out.
Now everyone always said that light is a wave, and British physicist Thomas Young thought that if he shone light at a screen with two small slits in it, in a similar way to the water waves, each slit would produce its own ripples as such. And we can see here, indeed, bright areas are where the waves have reinforced each other, and dark spots are where they've cancelled out. Now, if we shoot particles through a pair of slits, just like before, what do we think would happen? If we shot, for example, marbles through some slits, we'd expect to just see two identically shaped vertical lines on the screen behind. But when we do it with electrons, which you can just think of as really tiny marbles, we can see an interference pattern. But wait, interference patterns only happen when there are waves present.
You could turn it round the other way, so that matter, things like, say, electrons, things that we think of as definitely as being particles, could also be treated as waves, and you can throw those through the two slits as well, and they will interfere just as light does.
Physicists call this wave-particle duality. The strange thing is, though, just like with our water waves,
to make this interference pattern, you have to get something going through one slit interfering with something that goes through the other. And you can do this with particles, one particle at a time. And so this is where it gets interesting, because what you've got to assume effectively is that those particles go through both slits at once.
As well as quantum particles being able to be in more than one place at once, they can also do more than one thing at once. This is the equivalent of me being able to do the washing, clean the house, run my errands, and prepare the dinner all at the same time. Wouldn't life be a lot easier if I were a quantum particle? It's just a consequence of particles' wave-like nature. You can't pinpoint exactly where it is at any one time.
Waves, if you think about it, they're everywhere, right? Where's a wave? You know, if I have a wave in a shore, I can't say, the wave is particularly at that point, because it's inherently a wave-like object. I don't know where it is. I can't say.
It's not a physical thing that's spread out in space. Actually, what's spread out is a probability wave, a mathematical object where you can assign different numbers to different places in space, which is the chance of finding the atom were I to look there.
You can't really say what the atom is doing. All you can do is make predictions about the probability of it turning up at certain places. So the wave itself isn't really an atom. But still, so what's going through the two slits? It's not probability. The atom was on one side, and at a later time it was on the other side. It got from there to there somehow. How did nature do it? And that's the big dilemma.
In the quantum world, everything is a game of chance. You can't say anything for certain, and particles do some very strange things as a result of this probabilistic nature.
Yeah, quantum tunnelling really reflects this idea that we don't know absolutely where a particle is.
When you were waiting outside my door, you couldn't get in. If you were a quantum particle, you could. You'd be in here waiting for me.
Quantum tunnelling is like it's kicking a ball up a hill, and in the classical world, the Newtonian world, you'd have to give it enough oomph for it to go to the top of the hill and down the other side. In the quantum world, there's a certain probability that even if you don't kick it quite hard enough, it'll only go up halfway up the hill, but instead of rolling down, it'll disappear and reappear and roll down the other side of the hill. It's quantum tunneled through. Because you describe this, say, the atom by a probability wave, that probability wave is extended in space. And the probability wave can leak its way through the barrier. It doesn't mind. It's not a physical object. But what it means is there's a non-zero probability that the atom might be found on the other side. Now, it sounds just like mathematical gobbledygook, but in fact, quantum tunneling does happen, and in fact, it's the reason why we're here, because the sun shines because hydrogen atoms quantum tunnel into each other. That's what nuclear fusion is all about. They quantum tunnel into each other to turn hydrogen into helium. So if quantum tunneling wasn't true, wasn't real, the sun wouldn't shine and we wouldn't be here. But it's still very weird to try and explain.
Even spookier is a quantum mechanical effect called entanglement, where two or more subatomic particles, no matter how far they are apart, have their fates, their properties intertwined, such that doing something to one will instantaneously affect the other.
If you have a left and a right glove, and you put them in two boxes, and you move those boxes very far apart, you don't know whether the left glove is in the box that you've got or the right glove. You open it up, instantly you see you've got the right glove, instantly the one over there has to be the left glove. But that's not real entanglement, that's just your ignorance.
In the quantum world, the one you've got is truly both a left glove and a right glove at the same time. And when it does decide which one to be, the other one, no matter where it is in the universe, will change accordingly. What's the use of all this knowledge of how quantum particles work, though, if we can't even see it in the everyday world?
The very fact that devices like mobile phones are around, I mean, that ultimately is due to quantum mechanics.
3/4 of the gross domestic product of the United States relies on technology and industry that we wouldn't have were it not for quantum mechanics. That's how important it is. It's the most important theory in science. Quantum mechanics underpins the whole of physics, the whole of modern chemistry, because it describes how electrons fit around atoms and so fit together. Without quantum mechanics, we wouldn't have electronics, we wouldn't understand semiconductor devices, we wouldn't have the laser, we wouldn't have the microchip, the computer, we wouldn't have iPhones and iPods and CD players. So quantum mechanics, although it's a theory that's really weird, without it we wouldn't have understood nature down at the subatomic level. So it's everywhere, basically.
It's essential for our modern way of living. There are also some exciting developments on the horizon, such as the quantum computer, which could do certain calculations quickly that for conventional computers would simply not be possible.
If you have $1 million on your table, the best way to count it is not for you to sit and count from 1 to 1 million. You get 10 of your friends who you trust and you count it and you do it in parallel. Well, that's what a quantum computer does. It basically does a lot of calculations at once.
Quantum mechanics has a plethora of applications and has enabled us to drastically expand our fundamental knowledge of the universe and everything in it. But will we ever be able to truly explain all the weirdness of the quantum realm and all the phenomena that so harshly violate all common sense and intuition?
You figure there's at least an element of truth here. It may not be the final story, but there are a lot of threads of the final tapestry that are right in front of you. What's not clear is, for example, whether the final theory will have this element of probability to it. It may just be an intrinsic part of the world we live in. Then again, it may be an indication that there are, for example, other dimensions out there that somehow, when projected onto the world we live in, manifest themselves as this uncertainty. Who knows? I mean, it's fun to speculate about.
It's how everything works. It's the most fundamental science.
It's still a hugely important fundamental theory that probably has lots more to tell us about our universe.
I think there'll be more secrets.
And through quantum mechanics, maybe we will find the answers to even deeper questions about the universe. Or maybe it stops here. Maybe it's impossible to know any more.
In science, I mean, particularly over the last 20 or 30 years, you learn never to use the word impossible. Because things have happened, discoveries have been made, which you could not have predicted in your wildest imagination.
Quantum mechanics is weird. I don't think the weirdness is going away. But I'd like to think that sometime in my lifetime we'll sort it out once and for all.
We can't relate it to anything we're used to. If we don't find anything else behind all these strange goings-on, one thing is for sure. It's weirder than anything you've ever seen, stranger than any science fiction, down in the quantum world.